Hello, stats class. Here is the chart for chapter 11, and for 11.1 we did this column, and now we're going to take this sticker off and do the other two columns, which are about homogeneity and independence. So remember, this was 11.1, this was 11.2a and b, and this is 11.2c. We're going to combine it into one thing. So in homogeneity, we have two or more populations. I'm going to write that as 2 plus with an S at the end. 2 or more samples and one variable with many categories. That happens in both of these situations. And what we want to do for homogeneity is compare the populations to each other to see if they are homogeneous, which means the same proportions. I've heard that pronounced homogeneous also, but I think homogeneous makes more sense to me. And then independence is when we have one population and one sample, but 2 variables. So that's a major change. And we're comparing the variables to see if they're associated or independent. So it's sometimes called an association test. And the main difference between these two tests is the 1 sample versus 2 samples, but also the hypotheses are different. Everything down below is almost the same, so that's why this is all one big box down here, and for both, it's the same calculations. So the hypotheses for a homogeneity test are the distribution of whatever variable you've got is the same for all populations. And of course, you would want to name what your populations are. And the alternate is the same as for goodness of fit. It's that at least one proportion is different. You don't have to write it again if you don't want to. The null and the alternate for independence, the null is that they're independent. So the variables blank, and of course you would fill in the blanks with what they are independent. I should have put that on the next line, but I didn't. Or you could say there is no association. Because that makes it match what we've done before with the null hypothesis of there is no difference or everything's normal, everything's what we expect. That's what the null should say. The alternate is that there is an association between those variables. Or you could say they're associated. Do not use the word dependent. Do not use the word correlation because that's for quantitative only. So association is the correct word for that. And then, of course, these are both chi-square tests. This one's for homogeneity. And this is the chi-square test of independence, or sometimes it's called association. They're both correct names. Random, large sample, and independent are really the same for all 3 of these. And so I'm not going to write them again, although you can if you want to. They are the same. You're going to check to see if it's a random sample, or often with homogeneity, it might be randomly assigned treatments. I guess I could put that in parentheses. But really, it's the same for all 3. Large enough sample is all e's being bigger than or equal to 5. That's the same for all. The only difference is how you calculate the e's. So over here, you would do e equals the row total. Actually, you know what? I'm not going to write it here. I'm going to write it down there. I'm going to do that. We're going to write it in the calculations section, but you would check the smallest e. And then the independent less than 10% thing, also true for both of these also. So you don't have to write it again unless you want to. And then remember, if it's an experiment, you don't have to check the 10% rule. So I'm going to say or randomly assigned treatments. And that would be with homogeneity that you'd have an experiment. So that's the same. We don't need to write it again, right? The calculations are different. So let's talk about calculations. They're almost the same, but not quite. So the DF for both homogeneity and independence is the number of rows minus 1 in your two-way table times the number of columns minus 1. Expected value is found by doing the row total times the column total divided by the grand total, and you do that for each individual cell of the table, except technically you only have to do it as many times as your DF, and then the rest you could find by subtraction. Or if you're using the calculator shortcut, it does that for you, which is so nice. I'll mention that down below. This formula is the same. It's the sum of, this time I have room to write it out, so I'll write observed count minus expected count squared over expected count. You do that for each cell of the table, and then you add them all up. That's what the big sigma thing means. The calculator, again, will do that for you, but you should write out a few of them and put plus signs in between to show me that you know the formula. And then the p-value is either the calculator finds it or you do chi-square CDF. Chi-square and 999 and DF. So that's the same as before, and that's kind of comforting. So these are the same and these are the same. Calculator shortcut, this one's on both the TI-83 and the TI-84. It's just called a chi-square test. And you put your observed counts in matrix A. And then the calculator fills in matrix B with the expected counts by using this formula, and you don't have to do that. The conclusion is the same, so that's like super fast chart because it's so much the same as what we've done before. So that is the end of chapter 11, believe it or not. Homework is the review assignment, quiz is Wednesday, and then we move on to chapter 12. We are almost ready for final review. So exciting.